Hi, welcome back to another BeamNG World Editor tutorial. Today we're going to do a deep dive into a very important part of BeamNG.drive, which is materials, or more specifically the main.material.json file. Okay, let's talk basics. Most of what we see in BeamNG are 3D models, like physically see with our eyes. When a 3D model is created, the 3D artist assigns a material to the model, or parts of the model, so that when it's rendered, it can simulate light hitting the object and reflecting into our eyes, just like it does in real life. Without materials, models would be invisible. BeamNG uses a game engine called Torque 3D, which has its own built-in renderer simulating light sources like the sun, calculating how the light interacts with the material of the object. To make the render look realistic, the material can have several properties or maps that define how the light behaves. We've touched on these before, but some examples are base color, metallic, roughness, normal, specular, and emissive. Different engines have different material properties, and sometimes they go by different names like diffuse or albedo instead of base color. Originally, BeamNG used version 1 materials, which were primarily just color map, a normal map, and specular. They did have rudimentary versions of detail, color palette, and opacity, but much of it was hacked together. Introduced in release 0.23, we now have version 1.5 materials, which brings PBR, or physically based rendering, into the game. 1.5 still has the primary color map, it's now called the base color, and normals, but instead of specular, we now have metallic, roughness, and ambient occlusion, as well as better opacity maps, color palettes, and a brand new emissive and clear coat map. Let's go through the official BeamNG documentation for a quick refresher on what these texture maps do. We have 8 basic texture maps. Base color map is the diffuse color of the material, and the image format is RGBA. Base color detail map is an additional color map, which scale can be adjusted independently. The image format is also RGBA. Metallic map defines whether or not the material reacts to light like a metallic surface. This image format is grayscale. Normal maps add depth to the material by modifying how light reacts to surface normals. The image format is RGBA for normals, but the data is captured in a tangent space normal map. Next, we have normal detail maps. It's an additional normal map where the scale can be adjusted independently. This format is also an RGBA and is also a tangent space normal map. Roughness map is the degree to which the surface scatters light, affects the sharpness of reflections, and the size and intensity of specular highlights. The image format for this is grayscale. Next, we have opacity map, which defines part of the surfaces that are transparent. It requires a transparency option in the advanced all layers section, and we'll go into later. And the image format for this is grayscale. And lastly, in the basic texture maps, we have ambient occlusion. It's the intensity of environmental light on a surface, and the image format for this map is also grayscale. Next, we also have 3 advanced texture maps, which we've mentioned before. Color palette map. This assigns vehicle color presets 1, 2, and 3, depending on the use of the red, green, and blue channels of the texture. The PBR parameters of each color preset are multiplied over the existing corresponding PBR value in this layer, but it can also be used for static objects, and the image format is RGB for this one. Next, we have the emissive map. This defines which parts of the material emit their own light. The image format is also RGB. And lastly, we have the clear coat map that controls the clear coat effect. This is only used for vehicles as it's very performance intensive, but the image format is grayscale as well. So far, we've talked about how materials are assigned in 3D modeling software, but we haven't shown how we can actually get them into a game engine. Something needs to tell the engine how to render it, and that's exactly what the main.materials.json does. Main.materials.json files are the material definition files that tells the Torque renderer what materials are called, what material properties they have, like we discussed. Quick side note, I'm mainly going to refer to these files as material files, so I don't have to keep on saying main.materials.json files over and over again. In short, the workflow goes, the model is created first, the material is assigned, you build your material file, you set up your textures, configure shaders, and then you get an on-screen result. Okay, I think we've got the basics done. Let's go ahead and bring up a dev folder and we can see how these work in practice. So this is the level folder for the dev map East Coast USA. This is made by the developers of BeamNG.drive. In the folder structure for a level, you will typically find materials, models, and assets stored in an art folder. From there, they are usually categorized into subfolders for the types of object. So let's go ahead and look in shapes. And then if we look in these folders, we can typically find a corresponding main.materials.json file for that asset type, like this one in buildings. A couple of notes for the folder structure. The name of the material file can be changed if you like. It's not required, but you can make it sealandair.materials.json file or buildings.materials.json file if you want. The developers don't do this. They just keep it main.materials.json files. The important part is the suffix at the end, materials.json. The engine needs that to be able to map the materials properly to the level. You can also have multiple material files throughout your folder structure, but obviously they can't be two in the same folder. You can do what the devs do if you like and keep your material files separate in categorized folders, or you can merge them into one master material file. I kind of do a hybrid approach for my maps. I keep a master material file for all of the developers' materials. Then, if I make any custom textures, I keep those material files in the same folder as the model. So I keep my custom stuff separate and the dev stuff together. Lastly, make sure that there's not duplicates of the same material in more than one material file. For example, if you have a material called asphalt in one material file and then another material called asphalt in a different folder or file, the engine does not like that. There's a conflict there. Okay, so let's go ahead and open this file in a code editor. I use Visual Studio Code, but you can use Notepad++ if you like. Code. Relax, it's not that bad. This stuff is actually really easy if you just take a second to understand it. Okay, so JSON files. JSON, or JavaScript Object Notation, is a super lightweight programming language that was literally designed to be easy to read. So it works like this. These little curly brackets at the top are called an object. It's like a container that holds the code. It has a starting bracket and an end bracket. Then you have these blocks of code that you can collapse at different indentation levels if you like. The first one is called level 1, and then the second indent is level 2, third is level 3, etc. The materials in this file are listed by name on level 2. So we can see we have this building underscore glass underscore transparent, and then a bunch of other stuff underneath it. So yeah, this is how material definitions are stored, and we'll definitely go into greater depth of all these blocks during the demonstration later. Okay, a few JSON notes. The material names must match exactly what is in your Blender or your DAE file. One typo means an invisible mesh. If you have a lot of materials in your material file, you can collapse them individually if you like, or pro tip for Visual Studio Code users, you can actually fold them to level 2 by pressing Ctrl-K and Ctrl-2. The material blocks don't have to be in any order, but if you wanted to sort them using Visual Studio Code, you could press Ctrl-Shift-P, type Sort JSON, and select that option. Most of these material properties have default values. If a property is set to its default value, it won't actually appear in the JSON at all. It'll still work just fine, it just won't show up in the code. And lastly, if you edit and save any material in the in-game editor, the JSON will actually alphabetize all of its stage fields and generate null values for unused stages. This won't break anything, but it will make your code look a little bit messier, and it's good to be aware. Okay, so we made it through the boring but necessary part. Congrats. Now let's freaking make something. Okay, so we're going to make a new custom object, a new custom material to go along with it. And then we're going to add them to my template version 2 map I made in a previous video. So as we make this object, I'm going to explain how everything works. And let's go ahead and jump right in. All right, go ahead and open your 3D modeling software of choice. I'm using Blender. We're going to go ahead and take the default cube, and I'm going to turn it into a block of cheese. We're going to add a new material. Let's call it cheese. And let's go ahead and also rename the object and mesh to cheese as well. This is a good practice to get in the habit of. We can set the material base color here if we'd like, maybe something yellow. But I think for this demo, let's go ahead and use an image texture I found online. Heading to shading, we can actually drag and drop our texture image into the editor and then link it to the shader. I prepared a full texture set for our cheese ahead of time, but we really only need the base color texture for now in Blender. Go ahead and switch to viewport shading to the material preview, and let's see how this cheese block looks. Looks pretty good. So we can actually go to the UV editor if we need to make any tweaks on how the texture is projected onto the surface of the model. And then let's go ahead and save the file, and we can prep it for export. I'm going to use my Blender add-on tool called Mesh Tools to set up the hierarchy, which is needed to add an object to BeamNG. I'll go ahead and link the GitHub for that tool in the video description if you're interested in downloading it. I'm going to remove the automatically generated LODs. We don't really need those for this demo. They are good to use if you have a legitimate object that you're adding to the game. And I'm also going to apply transforms, triangulate, remove material nodes, and then lastly export as a DAE to our map folder. I'm going to put this file into the current levels template v2 art shapes folder. And we're going to go ahead and make a new folder called cheese, and we're going to put our model and our material files in there. Some quick 3D modeling and best practice notes. If you only have a single material on the object, it's a good idea to name it as the same thing as the material, so cheese for this example. Lowercase and underscores instead of spaces is also highly recommended for model/material and folder structure naming. Unintentional spaces can throw off an entire blocks of code. Highly recommended to create new folders for each asset you make. Not only does it organize everything, but it also helps prevent material files from being overwritten if they're generated again. Texture images for game engines can be a wide variety of sizes. Common ones are 512 by 512, 1024 by 1024. They're typically square aspect ratio, but you can do rectangular aspect ratios, for example, 256 by 1024. But all the textures need to be the power of 2. So power of 2 means that they're numbers that are exponents of 2. So for example, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, or 4096. The 3D file format BeamNG uses is called a collada file or a .dae file extension. It only uses the material's name, hence the need for material files. So any material nodes that you use in creating the model are not needed for the export. This is why I only added in the base texture. I just wanted to make sure the UVs lined up. It's important to note that the newest versions of Blender do not actually support exporting colladas natively. I'm using version 4.5, which does, so my add-on might not work in newer versions. Finally, I want to state that your goal in making a game asset is to optimize as much as humanly possible. That means removing any unnecessary layers, hidden objects, material nodes, unused channels, etc. Smaller file size equals quicker calculations and faster gameplay. As I mentioned before, out of respect for your time, I've already prepared a texture set here that we're going to use. I will do a follow-up video to show you how I made these textures and the texture cooker information if you want to check that out later. Because these are custom textures, we cannot reference them in the dev files, so let's go ahead and copy them over to our new cheese folder. Okay, so now that we've got our model made and exported and our textures moved over, let's go ahead and load up our level. Once loaded in, let's press F11 to load the world editor, and then click Window and open the Material Editor panel. Notice that if we search for cheese currently in the materials, nothing comes up. That's because the material file does not exist yet. So there's two ways that we can go about this, about creating a new one. We can manually create a new material in the editor, or we can go to the asset browser, and when we click on the models folder, the game will actually automatically generate a new material file for us with the correct name. So let's go ahead and show that second method first. Click on Window, click on Asset Browser. Once it loads up, find your custom level folder, then click on the cheese folder we just made, and now you'll see that there is a new material file created. Let's also drag the cheese.dae file into the level so that we can see what we're working with when we add the textures. Yep, so it's currently white. This is good. Default values for a blank material are white. Side note, if the material file didn't work, it would show the iconic orange no material debug texture, so we know that the material file is in fact generated. Now, when we return to the material editor, lo and behold, we should have the cheese material showing up in the search, which we do. If for some reason that didn't work for you, you can always create it manually. Like I mentioned before, the steps for that are click the new material button, name the material. Again, this must match exactly what you named it in Blender. In the map to field, enter the model's name, or you can actually pick from TS static to map it to a static object that you already might have in your level, or you can just leave it blank to be unmapped. Then lastly, you can change the path where you want this material file to be saved in. You can actually even pick an existing material file if it already exists in that folder structure, and it will safely add your new material to that existing file, appending it in. It's pretty cool. All right, beautiful. Your material now exists. Let's go ahead and start adding our maps in. Okay, so when we change any of these fields in game and then we save, we are literally modifying the material file. Just for comparison, let's put a sample material file that I made on the right side of the screen, and then we can have the in-game editor on the left. This sample shows nearly every possible field or tag you could use. Most materials are not going to have this many fields. Okay, let's break this down. I'm going to go one section at a time, and we'll be able to see how the object changes as each map is added. So first we have the material info panel. These define what the material is and what mesh it applies to. Name is the material name. Map to is the name of the mesh this material maps to. If it shows unmapped, the game isn't recognizing any assets that are currently using this material. It's okay, we can set that later. Directory is where the material file is physically stored. File name, this is not shown in the JSON, but this is the material file name. It's usually main.materials.json. Class, which is not shown in the editor, is usually material or terrain material. So you can see that in the JSON file. Also, persistent ID, which is not shown in the editor, is auto-generated. It's usually safe to ignore. Version, material system version, it can be changed at any time, so you can go back to version 1. There's usually really only one case that you'd want to do this, and we talk about it later. And then active layers, which shows the stages in the JSON file, are which layers and stages are being used. Internal name, which is not shown in the editor, is an optional alternate internal identifier. Lastly, the estimated size, not shown in the JSON file, shows the estimated total GPU memory that's used by all the textures in this material. All right, next we have stages and layers. So as far as I can tell, these are the same thing. They basically function like the layers in Photoshop or another photo editing software, and they allow you to stack multiple texture layers on top of each other. So this is how we can add grime or dirt texture on top of base textures. And this is what holds all of the texture maps that we have in this first stage or first layer. In the JSON file, the yellow brackets show the different stages. Important to note that most materials you'll use only have one stage. Okay, moving on to the main section. These are the basic properties. So first we have base color. This controls the primary look of the object. The base color map, which is, as I mentioned, albedo or diffuse color of the material. The path is where you set your image texture path. Let's go ahead and point this to our cheese folder and pick our base color, which is cheese_b.color.png. Next we have the color picker. This allows you to pick a color value that multiplies across the image. In the editor you can use the hex code, RGBA, which stands for red, green, blue, and alpha, or HSVA, which stands for hue, saturation, value, and alpha. The default color is white, and if we didn't have a texture, we could make this yellow, or if we wanted to make our texture affected by a different color, we could change the color, maybe darken it a little bit. We're going to go ahead and leave it white for now. Next, we have the UV layer. So this is an extra UV mapping option from the model. It defaults to 0, but it can be set to 1. There's two options here. This one's a little tricky. So recall how we customize the UV a little bit in Blender. We move things around. The standard map is 0, but if you wanted to make an additional UV map, you could do that in Blender and change the reference in BeamNG. So we'll leave the layer for 0 for now. All right, next we have the instance base color. This is a checkbox that when checked, it multiplies the color value by the sim object instance color value. This is a tricky one, but it's very, very useful. So we'll talk about this feature when we get down to the color palette map, but essentially, if checked, you can adjust the color value per object instead of having to make multiple materials with different colors every time. So for example, if you have a house, you can have different siding colors on the exact same house if you reference the siding material with this checkbox checked. The instance color field that they're referring to is in the inspector panel when you click on an object. Okay, next we have vertex color. So if checked, vertex colors painted in Blender will show on the model. This kind of works like the color, so if you already have a texture on it, it will multiply across the vertex color. There's also a material that the developers created called LOD_vertcol that applies vertex colors to LOD meshes if you set it up correctly. So unbeknownst to you, I actually secretly vertex painted the top of my cheese block in Blender. Maybe we got some mold up there or something. So if I turn vertex color on, you can now see that the top 4 vertices of my box turn black in the render. We'll leave it off though, because nobody wants moldy cheese. Well, maybe the French do. Okay, awesome. Base color is done. Let's move on to the next map. This is the base color detail map, similar to base color. Recall that this is an additional overlapping color map whose scale can be adjusted independently. Detail maps usually tile, and they're usually meant to add surface grain, noise, or dirt layered on top of the existing base color map. So let's go ahead and set this image path to our cheese_detail_b.color.png texture image. For scale, we've got 2 fields that control the horizontal and vertical UV tiling of the detail texture. Let's go ahead and adjust the scale so it looks good. Not too stretched, but not too tiled. Next, we have strength. This controls how strong the detail texture influences the final surface. So for strength, let's go ahead and make it pretty subtle. We also have another UV layer option that works the exact same as the previous map. Solid. So moving right along to metallic. Metallic map defines whether the material reacts to light like metal. It's a grayscale image, and let's go ahead and pick cheese_m.data.png from our folder. So for factor, this is a 0 to 1 slider for metallic strength. White means metal, very reflective, black means non-metal. And let's go ahead and set the factor to like 0.5. Pro tip here, if you don't want to use the slider, you want an exact value, you can actually press Control, click on the slider and manually set the value to whatever you want. Next we have another UV layer, no change needed here. And then next we have normals. Sweet. Normal maps add depth by modifying how light reacts to surface normals. So it essentially creates depth without extra geometry. Many of you are already familiar with these. Let's go ahead and set the path to cheese_nm.normal.png. And let's set the strength or intensity of the normal to maybe 0.8. We've got another UV layer, and then we come to the normal detail map next. So this is an additional normal map whose scale can be adjusted independently. This is basically the normal tied to the base color detail map. So we'll go ahead and set the path to cheese_detail_nm.normal.png. Strength and the UV layer, and good. Next we have roughness map. So roughness controls how the surface scatters light, affecting sharpness of reflections and intensity of specular highlights. We can set this to cheese_r.data.png. For the factor, this is a 0 to 1 scale where white is rough, which is diffuse lighting, and black is shiny. Because we have the map data, we can go ahead and leave the factor at 1. All right, next up we have opacity or transparency maps. So this is typically used for like glass or decals, fences. It defines which parts of the surface are transparent and see-through. Let's go ahead and grab our black and white cheese_o.data.png file. I decided to make the Swiss cheese holes see-through for this. So in opacity, white equals opaque and black equals transparent. Gray is partial transparency. And we can leave the factor at 1. There is one new option for instance opacity in this map. So similar to instance color, this allows the opacity value to be modified per object based on the instance color value in the inspector. And I guess you technically could use both instance color and instance opacity and have them checked, but it might make some strange results. You would have color change and opacity change happening at the same time. Okay, nearly done. Next we have ambient occlusion, or AO. So this controls the intensity of the environmental or ambient light on the surface. For example, it might darken cavities or brighten corners between objects. Let's go ahead and add our AO map, which is cheese_ao.data.png. Let's leave the UV layer alone. And okay, we did it. We finished the basic properties section, and we can see how insane our cheese looks. Really good. Okay, I have one more bonus tip. So for key PBR maps, we use 3 separate images for ambient occlusion, roughness, and metallic. However, we can actually make something called a combined map for these properties and optimize the material quite a bit. So how a combined map works is, since those maps are all grayscale, we can actually channel pack them into the different red, green, and blue channels of a single image. Red would be ambient occlusion, green is roughness, and blue is metallic. And you can do this in your photo editor as well. Then we can set the maps to reference the same texture path for the multiple map slots. It's pretty freaking cool. It saves space and computations. Okay, now we're on to the advanced properties section. We've gotten the basic properties out of the way. These are the advanced properties. This first one is called color palette. So the base color palette. So this map assigns instance color 0, instance color 1, and instance color 2 in an inspector view to the red, green, and blue channels of a texture, respectively. This one's a bit tricky. We touched on this before with the instance color checkbox in the base color map, but essentially what this does is it expands that one instance color to now 3 instance colors tied to the RGB values of an image map. To demonstrate this, I made an image that has 3 splotches of the color red, green, and blue. Let's go ahead and set that path to cheese_c.color.png. So now when I click on our object and if I go to the Inspector tab, you can see how I can adjust the areas that are RGB with the 3 instance color fields. This is actually what is used for vehicles when you change the 3 colors in the vehicle config window. You can uncheck the checkboxes to disable the palette on specific maps if you'd like as well. All are enabled by default. Sweet, so the next section is called emissive or glow. The emissive map defines which parts of the material emit their own light. White is glowing, black is not, and the default is white. Emissive maps are pretty cool because they essentially make the material render at night. This is an area you don't see much in dev assets. It's primarily used for traffic lights and a few other things. Let's go ahead and set the path to cheese_e.data.png to show this off. It's kind of a wild map, but as you can see, if I set the time of day to night, the material is still visible. Options are factor, which can change the color or intensity of the emissive light in RGBA values. Instance emissive, which is similar to instance opacity or instance color. If checked, the emissive factor color is multiplied by the instance color 0 from the inspector. And then we also have vertex color, similar to vertex color on the base map. If checked, the vertex color is multiplied by the emissive color value. One bug note, if you add any file to the emissive map slot, it will default, it'll overwrite to full white emissive, and this might make your material look washed out or really bright. So if that ever happens, all you got to do is manually change the factor to black to correct it. Okay, last 2 maps. We're almost done. Clear coat and clear coat bottom normal map. We are making a car, so we don't have a texture for this. But this map adjusts the clear coat effect. It's a grayscale texture. The factor is the intensity of the clear coat effect, and the factor roughness is the reflectivity of the clear coat. It also has a UV layer, and then you have the clear coat bottom normal map. So this allows an extra normal map beneath the clear coat layer. And the only parameter here is strength, which is the intensity of the normal map. Okay, that's it. We made it. All texture maps complete. Thanks for hanging in there with me. There's one final checkbox at the very bottom that's called the anisotropic filtering. It's checked by default, and I usually just leave it checked. It significantly sharpens textures on surfaces viewed at oblique angles, like roads or walls that are stretching off into the distance. Okay, moving on to the optional sections below, we have animation properties. These are purely UV space shader animations. Nothing here moves geometry or touches physics, so they're just mathematical manipulations of the texture coordinates, the UV coordinates over time. You're animating the surface illusion, not the actual mesh. Okay, so the animation section uses animation flags to track which animations are active. So in the JSON, it's called anim flags, and it will have a corresponding number. So the best way to add this is just to check your boxes in the editor, and it will automatically come up with the correct combination for the animation flags. Okay, first we have rotation animation. So this rotates UV coordinates around a pivot point. You can check the box to enable, and then you can also set the rotation pivot offset. It's a 0 to -1 value that offsets the rotation center. So for example, 0.5, 0.5 is dead center. 0, 0 is the bottom left. Next we have speed. That's a -1 to 1 value. Positive means one direction and negative means the other. Next rotation type is scroll animation. So this linearly shifts the UV coordinates over time. You can check the box to enable, and then you can set the scroll direction, which is -1 to 1. Some examples of this would be 1, 0 is horizontal scroll, 0, 1 is vertical, or 1, 1 is diagonal. Next, we can set the speed. So this is a 0 to 10 value, self-explanatory. Next section is wave animation. So what this does is it distorts UVs in a periodic function. So check the box to enable it. The different types of waves are sine, which is smooth oscillation, square, which is hard snapping, and then triangle, which is a linear rise and fall. Scale scales the UV input before the wave math. It changes how spatially dense the wave patterns appear. The amplitude is a 0 to 1 value. It's basically the strength of the distortion. So small values like 0.01 to 0.05 are subtle, whereas large values get chaotic quickly. Frequency is a 0 to 10 value, and it's how fast it oscillates. Next section we have is image sequence. So this actually treats the texture almost like it's a sprite sheet animation. So you can turn it on by the checkbox. Frames per second is a 0 to 30 value of your playback speed. So this would be 30 frames per second, 15 frames per second, etc. And then you have your frames, which is a 0 to 100 range. That's the total frame count in the sheet. Okay, this next section is the advanced all layers section. And this was really just the settings for opacity and reflections. So these are the settings you want to tweak when you add an opacity map in the basic properties section from earlier. There's a fairly major bug here. So in Materials version 1, you didn't actually need to have a dedicated opacity map because the renderer could actually use an alpha channel in your color map, your RGBA color map, to determine what was transparent and opaque. So essentially the map for the opacity already existed in the alpha channel of your color map instead of having its own dedicated map. So here's your options. If you're using version 1 materials and you have an alpha channel in your color map, you just need to turn on the alpha clip and adjust the alpha clip threshold. If you're using version 1.5 materials like I am, you do need to have a dedicated opacity map texture. No alpha channel in your base color image is required. It currently does not work. And then after you have your dedicated opacity map, you just need to turn on alpha clip and threshold again. The rest of the settings are good to know, but they're very use case specific, so your mileage may vary. Mess around and see what works for you. First, we have the alpha blend mode. I'm going to fly through these pretty quickly because they're usually not that relevant. So none is fully opaque, no transparency. Pre-mul alpha is standard transparency. The RGB values are pre-multiplied by the alpha. This is best for most transparent materials. Next, add is additive blending. This adds material color to whatever's behind it, so it's good for fire or holograms or lens flares. Add alpha is the softer version of add. It respects the alpha channel. Next, we have lerp alpha. This is your standard see-through transparency via linear interpolation. This one's the most commonly used, and it pairs nicely with your opacity map. Next, we have mul, which is multiplicative blending. It darkens what's behind it. It's useful for tinted glass or shadows. And then lastly, we have sub, which is subtractive blending. It removes the color from the background. Moving right along, we have Z-write. This controls whether the material writes to the depth buffer. It's usually disabled for transparent objects to avoid sorting issues, or enabled for opaque ones. Next, we have receive shadows. This is whether shadows from other objects can appear on the material. So you'd want to turn this off for glowing or holographic materials. Next, we have alpha clip. This one's a big one. So this is binary transparency. The pixels are either fully visible or fully invisible. This is really good for fences, leaves, and most transparent cases. Remember that in version 1.5, this requires an opacity map to be used. And we also have the alpha clip threshold. This is a slider or a cutoff point where the alpha clip is on. It's a 0 to 1 value range. Below the threshold equals invisible, or above it equals opaque, and the default for this is 0.5. Double-sided renders both front and back faces. This is really good for leaves or thin details, but it costs on performance. Invert backface normals, inverts normals on the back faces so the lighting looks correct, and this only really applies when double-sided is enabled. Next we have cast shadows, so this is just a checkbox for whether this material casts shadows, pretty self-explanatory. Next we have reflection mode, so your options here are level or cube map. Level is much prettier, it actually reflects what's in the physical level, but it has a pretty significant performance cost. It really should only be used on vehicles. And then we have the cube map. This is pretty common in most game engines. What this does is it uses 6 images, the front, back, left, right, up, and down, to simulate the reflections. They're pre-baked images. And then in the cube map section, you can select which cube map file you want to use for low roughness objects like windows. Okay, finally, we have the last section, which is the additional info section. This is where we have material tags like road or the creator's name. These essentially make it easier to search for that material. You can search by tag. And some tools actually need a material tag for the material to show up in it. For example, the decal road tool, one of the tags it needs is quote road and path. If you don't have that tag, the material will not show up selectable in the decal road tool. We also have ground type, so if this material is driven on, you can select the ground type for the vehicle interaction. So this would be like snow or grass or dirt. Essentially, it uses the library of predefined ground types for this. And then lastly, we have the annotation map or annotations. So these are optional developer-only annotation data. I haven't found a way to actually add to them, so they're just kind of there for the devs to use. We can leave the tags empty for the demo. So yeah, that's the deep dive into materials. We can see how this has all come together in a complete materials file. It does look like a lot, but once you understand the structure, it really does become second nature. As always, if you have any questions, drop them in the comments, and I hope this helps. See you next time.